Okay, here we have a block sitting motionless on a 20-degree incline. Since it's sitting motionless and nothing else is acting on it, there has to be some static friction at work here. Well, static friction acting at least. So again, I have the weight down and I have the normal force up. Static friction is stopping it from sliding down, so static friction must be pulling up the ramp, and I don't know that it's at its maximum value, so I'm just going to call it F sub S at this point. I'm going to break up my mg into components. You could do it the other way. There's no acceleration here, so there's no reason you have to do it one way or the other, but if I do it parallel and perpendicular to the axes, I only have to break up one vector into components. The other way I have to break up two. So it's just a little easier here. And I'm solving for the static friction force, so I'm going to go ahead and not break up the thing that I'm solving for. Just pick my axes that way and make it easier. So I'll call down the ramp and out of the ramp positive. And yes, we tilted the axes because of what I told you. So perpendicular to the ramp, I have n pushing out. I have mg cosine theta pulling in. It's balanced all around, so 0 for both f-nets this time. I have mg sine theta pulling down the ramp, opposed by F sub s. Again, I can't call it mu sub Sn because I'm not sure that it's at its maximum value. So solving for the value of the static friction force, pretty easy. So our 2 kilogram block times g times the sine of 20 gives us 6.84 newtons. Now if we change the situation to say that this is the maximum angle at which the block will not slip, then that tells us something about the static friction force. So I don't need any if the angle is 0, but as I bring it up and up and up higher and higher, the static friction force has to get bigger. So at some point there's a maximum angle. So if 20 degrees is that angle, what I'm saying is that the static friction force is at its maximum value, which is mu sub s times n. And so I can go back to this, it doesn't change the net force equation other than that. So I can go back to my previous result. All I need to do now is substitute for n. I'll do that from the other equation. So the m's go away, the g's go away. And mu sub s is sine theta over cosine theta, which is tangent theta. And tangent of 20 degrees is 0.36. So notice that at the end of the day here, we have two things that don't have units, so the units work out okay. Notice also that the mass doesn't matter. The mass actually hasn't mattered yet for any of the 4 problems we've done. The mass has not made a difference at all. That's because all of our forces have, they all get bigger if you make the mass bigger, but then the m and ma also gets bigger if you make the mass bigger. So those two effects have canceled out.